Okay, so today we're going to cover kind of an extension of what we talked about last time. Last time in section 15.4, we talked about using a definite integral to find the area between the x-axis and a curve. Okay, and we talked about the fact that areas under the x-axis, if you're going to do this, are going to come out negative. So if you want to find the total area, you've got to graph the function first and see if it dips below the x-axis. Well, in this section, 15.5, we're going to extend the concept to find the area between curves. Okay, and these have some business applications that we'll talk about later on in this session. Okay, where one curve may represent one thing and another curve may represent something else. Okay, and the difference between them tells you something. All right, so we're going to start practicing by going through my class notes. I'll still use those as a base, and then we'll jump out of the class notes from time to time to either to work on problems ourselves, like a U-try problem, and I'll bring up Desmos, okay, as the graphing tool. I also have a calculator emulator, okay, so again, you're free to use whatever you like. If you want, I can show it to you on the TI-84, but actually I'd prefer if you use Desmos because it's easier. Okay? It's an easier tool to use. We can use both. So again, let me just start sharing my screen with you and we'll get started. Again, from time to time, I'll be pulling up the chat. So if you have any questions at all, just type them in the chat, okay? Okay, so here are the notes for this section. And again, you have these notes in your course. Interested in the area between curves, okay? Let's say savings from a manufacturing process that you've implemented in decline over time. Okay, so maybe you put in some new equipment, the new equipment gets older, and so the savings that you originally got from putting in the new equipment start declining. Okay? And let's say at the same time, the costs of that manufacturing increase. Suppose you want to compute net savings, okay? So what you would have to do is you'd have to subtract your costs from the total savings. You can think of this as being the difference between these two curves, right? So basically, if you want to represent your savings as f of x, your costs as g of x, right? And you can think of f of x and g of x as approaching each other, right? Because we said the savings are decreasing at the same time the costs are increasing. You can think of your net savings as the difference between the area under f of x, okay, minus the area under g of x, okay? Think of it this way. If you use the definite integral to find the area under f of x, that goes all the way down to the x-axis. Well, if you take the area under g of x, that also goes down to the x-axis, and you subtract that from the area under f of x, you get the area between the two curves. It's like a netting out, okay? So the way you're going to do that is take the definite integral of your top curve, in our case it's f of x, and subtract the definite integral of your lower curve. Okay, and in our case, that's g of x. Okay, so again, as long as these are continuous functions, and f, the y values on f are always bigger than the y values on g, like here. Okay, the area between the two curves from a to b is given as this expression. Okay, it's the definite integral from a to b of f of x minus g of x, top minus bottom. Okay. Let me just stop and ask, does this concept make sense? Okay, does the concept make sense? Just check in if you would, yes or no. Does the idea of subtracting the second lower integral from the top one make sense? Because again, remember, definite integrals give you the area between your curve and the x-axis. So I'm doing a subtraction to net out the difference. Anybody else? Okay, good. I have 2 yeses, and I kind of think there are 5 of you on. Good. All right, glad to hear it. Glad to hear it's clear. Okay, so let's take a look at some examples. All right, and again, we're going to start with the plain math book type examples where we're just doing a problem without context, okay, just to develop the skill. So a question might say, find the area bounded by f of x equals negative x squared plus 1 and g of x equals 2x plus 4, okay, between x equals -1 and x equals -2. Again, they're showing you these as vertical lines, but you can think of them as bounds on the integral. Okay? Now you need to graph these first because remember, you need to figure out which one is the higher graph. Okay, so I'm saying graph on your TI-84. You can also graph with Desmos. Okay, so you can see which one has greater y values, which one's the top function. So in my case here, the linear function g of x is going to have higher y values. Okay, see up here, this is g of x. Here's f of x down here. Okay, so I've shaded in orange the area that I'm trying to find. Okay, it's between the top curve, g. Take my integral, I'm going to plug in the values here. Okay, so here's my upper curve, g of x, minus my lower curve. Please note your lower curve is in parentheses. The reason for that is you want to make sure you subtract all of the terms in the lower curve from the terms in the upper curve. So take a look at the algebra here, okay? I'm distributing my negative sign. So I'm going to wind up with minus a negative x squared. Down here, that gives me a plus x squared and minus 1. Okay, the 4 from the upper curve minus 1 gives me a 3 down here. And there's no x terms in the second curve. So the 2x from the first curve just comes down here. Okay, so I've done the algebra of distributing my minus sign. And now here is the new function that I'm going to be finding the area of. Okay, so let me just stop here. Does the algebra here make sense? Okay, how are we doing with the algebra? Okay, everybody understand that I distributed the negative sign on the second function. Okay, if you would, please just check in with a yes or a no, okay, so I know whether or not to re-explain things. 2 yeses. How about the rest of you? Is this making sense? The lower curve from the upper one. Right, so I'm subtracting negative x squared plus 1, 2x plus 4. Anybody got questions on it? This is a good time to ask if you've got questions. Okay. All right, so the next thing I'm going to do is actually perform the integration. So remember, I take the antiderivative of the function, and then I'm going to evaluate it at the upper bound minus lower bound. Okay, so if I integrate x squared, I'm going to get x cubed over 3. Remember, add 1 to the exponent, divide by the new exponent. This is going to be 2x to the first, so I'm going to add 1 to the exponent to get 2x squared, and then that will be over 2. Okay, these 2's cancel out, and I'm just left with x squared. Right? This is like 3x to the 0. Remember, I can think of 1 as x to the 0, and then add 1 to the exponent. So I get x to the first over 1, which gives me 3x. Okay? Anybody, any questions on the integration? Is the integration okay? Are we okay with that? Everybody good with the integration? And I'm sorry to keep bugging you because, again, I can't see your faces. I can't tell if you're struggling with anything. So just let me know. All right. Then, according to the fundamental theorem of calculus, see this evaluation bar? Expression when x is 2, that's this part here. And then I'm going to subtract the same expression. Notice it's in parentheses, okay? Because I want to subtract all of the individual terms, okay, at -1. This is purely a calculator issue. You just type this in on your calculator. I can kind of walk you through the steps a little here. 2 cubed is 8, so I have 8/3. 2 squared is 4, 3 times 2 is 6. So here's the upper bound evaluation. Okay. And then here is the lower evaluation. Remember, whenever you cube a negative number, it stays negative. Okay, whenever you square a negative number, it becomes positive. So this becomes +1. And then 3 times -1 is -3. So I'm showing you an intermediate step here. And then once you're done, okay, you just, again, I'd start right here, type it all in on the calculator, okay? And then, again, let the calculator do the work for you. Okay? So again, it would be great if you have your calculator handy. Okay, try the evaluation yourself. See that you get 15. Okay? The evaluations yourself. Okay, I want to make sure everybody is comfortable with this. Okay, because again, you're going to have to keep doing it over and over again. Remember, on your TI-84, okay, they're kind of got it, what should I say? You kind of have to fake this out if you want to do it on your TI-84. I showed you that your TI-84 does definite integrals. Okay, so let me kind of show you how this would work. Okay, but I'll wait a minute for you to try cranking through the algebra yourself before I move to the TI. I'm going to ask, is it okay to show, I'm going to do this on the T. Is it okay to show you how to do this? Now remember, okay, it's a calculus class. I have no problem with you leveraging technology at all, but it is important that you are still able to reproduce these steps, okay? Or at least know how to put them into a TI. What do you think, folks? Is it okay to show you how to do this on the TI? Just give me a yes or a no, or no, I'm still working. Just let me know what's going on. Okay. Right. Anybody else? Okay, I've got 2 yeses. Let's switch to the TI and I'll show you how it works. Okay, so here I have my TI emulator. Try to get myself out of the way. Okay, so you go into y equals and you're going to put in the 2 functions. So I had 2x plus 4 as my first function. And then I had negative x squared plus 1 as my second function. All right, I'm going to try to graph those on a standard window, Zoom 6. Okay, and again, you can see I have, here's the linear function, which is higher. Here's the quadratic function, which is lower. And I want the area between -1, which is right here, and +2, which is, well, remember, if you use the TI's integration and the x-axis, right? So it's not going to net these out properly if I use that function. So here's what you have to do to find the area between curves on a TI. I'm going to go in my y equals, and I'm going to mute the quadratic. Okay, that means I'm going to turn off the graphing. The way you do that is you back over the equal sign and hit enter. Then when you graph it, you'll just see the linear function. I'm going to find the area between the linear function and the x-axis. Okay, so I'm going to use second, trace, and then integral, which is number 7 down here. And I'm going to use the same bounds that were on my integral. So I want to go from -1 on my lower bound to +2 on my upper bound. And it tells me that total area is 15. Okay, so that's kind of interesting. Okay, then I want to find the area with my quadratic on. So let me do that. I'm going to go here. I'm going to turn off my linear. And I'm going to turn on the quadratic. Now I just get the quadratic, and I want to know the area under that curve, between that curve and the x-axis, between -1 and 2. So I'm going to do second, trace, okay? And then I'm going to go down to intersect. I'm going to go from -1 to +2. Okay? And what it gave, okay? It basically said the area is 0, okay? Because again, these two pieces net out, okay? So when I did the subtraction, I wound up with 15 minus 0. So that's where I got the area of 0, okay? So you have to realize doing this on the TI is a bit tricky, okay? So let me ask, does the TI process make sense? So again, you basically find the area under the top curve, then you find the area under the bottom curve, you subtract one from the other. Again, this is meant to be a way to check your results, okay? Ideally, you can crank through the calculus part and get the answer, okay? So you can see here when you're subtracting areas between two curves, it doesn't matter so much that you get an area below the x-axis. It'll all net out anyway. Okay? So again, can I do it again quickly? Okay, sure. Show it again quickly. In here in y equals, I have both of these things graphed. And what I was showing you is the equal sign is what controls whether or not something graphs, okay? If the equal sign is highlighted like these two are, okay, when you graph the functions, they'll both graph, okay? Now what I want to do is I want to go in here and I want to turn them off one at a time. The upper function's the linear function, so I want to graph that first. So I'm going to turn off the lower function. So let's graph the linear function. If I want to find the area under that, that's on my calc menu, which I get to by second trace. And then number 7 down here is the definite integral. I'm going to choose 7. And then it's asking me for the lower and the upper limits on the definite integral. So those were -1 for lower, +2 for upper. And it says the area between those limits under this curve is 15 square units. Okay. Now, ideally, what I'd want to do is graph the lower function and find that area between the x-axis and the curve and subtract that from this. Okay, so I go back into y equals. Okay, I'm going to turn off the linear function by hitting the equal sign, and now you see it's not highlighted. Go down here to the quadratic, turn that on. Now that one will graph. All right, and then I want to find the area between that curve and the x-axis between -1 and 2. So I'm going to do second, trace, definite integral is number 7, from -1 to. Again, you see the area has netted out. You can see it shaded something. What it's telling you is this little bit up here is equal in area to the part that's below the x-axis. So the net area from the second curve is 0. So if I wanted to find the area between these two curves, I take upper area 15 minus lower area 0 and get the 15 that I got when I cranked through the actual calculus. Okay, is this better? Is that right? Anybody got questions on the process? Okay. I want to make sure you technology process for doing this. Okay. Make sure you can get the answers you're supposed to be getting. All right. So let's see if you can try it. So I'm going to bring up a U try. Okay, so I have this over here. Area between curves. You must graph the curves first. The integral of the top curve minus the integral of the bottom curve. So I'll say it's integral of the top curve minus the integral of the bottom. If the two curves cross, you have to split where they cross. We didn't get to that yet. Okay. So why don't you try this one? Okay. Try it yourself. Okay. What I'll be while you're working, okay, is I'll be graphing it in Desmos. I'll put the graph in this Word document, and then we can work on the calculus part together. But I want to see if you can try to do this yourself, okay? So take a minute, okay, and copy down the problem, okay? Copy down the problem now. Again, I don't care if you do it with calculus. I don't care if you do it on the TI. Just figure out how to do it, okay? And then I'll show you a couple of different ways, okay? All right. Okay. Um, Mary, how is it not working? I'm going to move off this screen onto my TI. Okay. What are we doing? Anybody getting a result? Okay, Yesenia got 4.5. Anybody else get that? Okay, if you take a look at what I have on the screen here, I graphed my two functions. And again, the quadratic turned out to be the height of the two functions. The y values were larger. So here's the area between the quadratic graph and the x-axis between -2 and 1. That turned out to be 9 square units. Okay, here's the area under the lower function, okay, that's the linear between -2 and 1, and that was 4.5 square units. So in order to net out the area to two curves, take this higher area, 9, minus the lower area, 4.5. Okay, if you wanted to do this with calculus, okay, you'd have to do something like this. You'd have to say from -2 to 1 on the integral, and then you'd have to have your upper function, which is the quadratic. So you'd have to say 4 minus x squared. And then you'd have to subtract the linear function, which is x plus 2. Okay. And again, that whole thing is going to be the dx after it. Okay, so this whole thing should be maybe in brackets. Okay. And then you're going to need to do a little bit of algebra on it. So let me see if I can at least copy the integral sign. It's not. Insert another function. Okay, and again, that's from -2 to 1. Okay, and then doing the algebra on it, you can see that I'm going to have 4 minus x squared minus x minus 2. So that's going to be -x squared. And again, I'm just combining like terms here. I'm not doing anything fancy. Okay, this x will be negative. Okay, and then this will be a -2 from before, so this will be +2. And again, the whole thing in here, we'll put around parentheses and put a dx out here. Okay, so then if I actually do the integrating, okay, -x squared, okay, realize the negative sign isn't going to go anywhere. Okay, so that'll be out in front of this. So negative sign. The x, I'm going to increase the exponent on that to a 3. Okay, and then put that over 3. So that's the integral of the first term. Okay, then I have x to the first. I'm going to increase the exponent on that. That's going to become x squared over 2. Okay, and the last term is just a plus 2 times 1. I can think of 1 as x to the 0. Increase the exponent on that, you get x to the first over 1. So this term just becomes plus 2x. Right? And then I'm going to evaluate that. Again, there's no really good sign here. So let me just put it in brackets if it will let me. Okay, and then I'm going to put the bounds of evaluation from -2 to 1. Okay, so again, I'm showing you the longhand calculus way of doing this, and we should get 4.5, hopefully. Okay, so I'm going to take this at the upper bound. That means I'm going to put in the 1. Right, so everywhere I have an x, I'm going to put a 1 in. Right, and then I'm going to evaluate it again, but this time I'm going to put brackets around it. Okay, and I'm going to put in the -2. Okay, the most common mistake people make with this is with signs. Okay, so because it's negative, I'm going to have to put my x in parentheses. Okay, And then what we just do is we're just going to take a look at what comes out of this. Again, I'm helping myself with my calculator here. Okay, so the first one, okay, if you cube a 1, okay, or you raise 1 to any power, it stays the same. So this is going to be negative minus 1/2 plus 2. And that gives me 7/6. Okay, so hopefully you got that. Right? Here's this minus sign I'm dealing with now. And now I'm going to try to evaluate this whole second expression. Okay, so I have a negative 2 cubed over 3 minus negative 2 squared 2 minus, and that's going to be 2 times negative 2. So this gives me okay, and hopefully when I add these two fractions, I'll get 4.5. Let's see. And yes, I get 4.5. Okay. Okay, so this is how you do it by hand the long way. Okay. Okay, with the long way. You kind of have to be able to handle both, but there's no reason not to use technology to help yourself. Okay. So if you would just check in briefly and let me know if you're okay with what I have here on the page, or if you have questions about it. Okay, just type yes or no or okay. We're good with it. Fantastic. With the calculator way, how did I get the fx d of x? Okay, so basically the top function is what you're asking, Nancy. Okay, so let me go back to the calculator real quick. I want to make sure I just save this file. Okay, here's the calculator. Again, all you need to do is basically go into y equals, graph your two functions, and remember I showed you the trick of turning one off or the other. Okay, so if you want to graph just the quadratic, which was our f of x, you that graph by backspacing over the equal sign and making it highlight, okay? So again, it's just you keep hitting enter. Enter turns it off, enter turns it on, enter turns it off. See, like that, right? The other graph, though, you want to turn off. So I'm going to hit enter on that one. Now this is set up to graph the quadratic, okay? So I'm going to graph it, all right? And then all I'm going to do to get the area under between that curve and the x-axis is second, trace, and then it's the numbers down here, the one with the integral sign. Okay, that's a definite integral, and it asks you for the limits. Okay, so you're going to type in your lower limit, which I think was -2, and my upper was 1. And it will tell you what the area is under that curve. Okay, is that clearer? Okay, again, the idea is to learn all the different tools that will help you do this. They should all tell you the same answer, okay? But you should be able to seamlessly switch from one tool to the other when it doesn't suit your needs anymore. Okay? You want to get to be a proficient tool user. Right? So is that better? Any other questions on this problem? Let's go back to the notes and then let's look at some other situations. Okay, so here was our first example. Let's look at this one. Okay. Find the area between y equals x to the 1/2. You can think of that as the square root of x, and y equals x cubed. Notice there are no x equals here. They aren't giving you the bounds of the integration. So that must mean that the two curves create a closed area between them. Okay, otherwise the problem wouldn't make sense. So the first thing you want to do is graph it. Okay, since no limits are given, graph both curves and determine where they intersect. On your TI-84, remember that second trace intersect. Okay, and basically I got the point of intersection as 1. The curves intersect at x equals 1. Okay, so they become my bounds of integration. Okay, I'm going to switch to Desmos to show you this one because it's much easier to find points of intersection on Desmos. Okay, so let me get over to Desmos. And again, one of my functions was y equals x to the 1/2. Okay, so there I have it. Right, there's my first graph. And then my second graph is y equals x cubed. Okay, you can see the area I'm interested in is way down here. That's not a problem on Desmos, right? Because Desmos, you can just zoom in. You center your screen and just zoom in. Okay, this is more of a pain in the neck on the TI because you have to realize you've got to reset your window. Okay, so here are my two curves. Okay, Desmos also nicely color coordinates them for you. So the green curve is the square root. That's the upper curve in this situation. The blue curve is the cubic, okay, and that's my lower curve. Okay, so my f of x, my upper curve is the square root. My g of x, my lower curve is cubic. And again, all I have to do to find where they cross is to just click on those points. Okay, so this tells me very quickly my upper curve's my square root, and the bounds on the integration are from 0 to 1. Okay, is everybody okay with the Desmos graph? Okay, again, I want to show you a bunch of different ways to do this. Again, Desmos is an app. You can certainly use Desmos on your phone. You even got the pinch and zoom feature there. You don't even need to zoom in and zoom out. You can just pinch and zoom. Okay, so are we okay with this? Right. Again, I want to make sure you understand where the integration bounds came from. Okay. They're where the two curves cross. And also, okay, why I'm going to be using the square root as the upper curve. Okay, so before we move, let's just say questions. Anybody got questions on any of this? A couple of no's, we're good. All right, I'm going to move back to my notes. Okay, so again, you would use second trace intersect on your TI to find this point is 1, 1. Okay, and then you have your bounds on your integral, okay, from 0 to 1. So again, the square root was the high curve throughout that integral. I'm putting it first. And the cubic was the lower curve. That's why it's second. Okay, bounds on the integral go from 0 to 1. And again, here's the calculus method. I'm adding 1 to 1/2 to get x to the 3/2 over 3/2, adding 1 to the cube, get x to the 4 over 4. Remember, divide by 3/2 means multiply by 2/3. So here's the expression I'm evaluating. Okay, I'm plugging in a 1 for the first, for the upper bound. Okay, so this is going to give me pretty much 2/3 minus 1/4. And then when you plug in a 0 here, you're going to get nothing, right? Because 2/3 times 0 is 0. 0 over 4 is 0. Okay, so 2/3 minus 1/4 is 5/12. Okay, let's see if we can get that value, by approximating it on the calculator. Okay, I'm going to go back here. The answer from calculus is 5/12. Okay, so I'm going to go over here. I'm going to put in my two curves. Right, and the first curve I'm going to put in, I want to make sure both of these, both of these are set up. So I have x to the 1/2. Right, and then I have x cubed. Right, and let's graph them. I think I'm set up for a standard window, so you're not going to see much. See the little bit down here I'm interested in? So I'm going to change my graphing window to go from 0, how about -1 to 2? That should be interesting. Okay, so window on x is going to go from -1 to 2. Okay, and I'll have my y window go from -1 to 2. Okay, that should be a little more interesting. Okay, and now you can see the part I'm trying to find. Now I'm going to use the same technique I used before by turning off one function at a time. I'm going to start with the upper function, the blue one. Okay, so I'm going to turn off the red function and find the area from 0 to 1 under the blue curve. So turn off the red one. All right, and then I'm going to do second, trace number 7, go from 0 to 1. Okay, so that gives me this value, and unfortunately I need to write that down. I have to make a note of that somewhere. I'm going to try the red curve, so go back in here, turn off the blue curve, turn on the red curve. Okay, and see if I can find the area between that, okay, and the x-axis between 0 and 1. So second, trace for 7, lower limit 0, upper limit 1, and that gives me 0.25. Okay, so now I have to do some clunky math. Okay, I have to get out here and I have to type in the value that I got for the first one, which was 0.66668013 minus 0.25. Okay, and again, you can see I get this. Okay, I don't think I'll be able to math frac it, but I can try. Nope, it still says that. Now my answer was what, 5/12? So let's see if 5/12 is close to this. Yeah, you can see it is pretty close. But now what you're seeing is a limitation of the calculator method. Okay, my exact answer, this is an exact answer, 5/12. This answer is close, but what happened was the calculator did some rounding. Okay, namely when I found the area under that first curve, that square root curve, I didn't get an exact answer. Okay, the calculator approximated. Okay, so everybody see the limitation of the calculator method. Okay, see the limitation? So my answers are close, but they're not exactly spot on. So this is another reason why you want to make sure you can do this, okay, yourself, okay? I'll also draw your attention to things like Symbolab that will work integrals out step by step, okay? If you're truly stuck, fire up Symbolab and see how to do it step by step. But again, everybody ought to be able to handle the basic calculus that we're doing. Okay? If there are no questions at this point, okay, I'm going to move back to my notes. So anybody got questions? That's good. Let's go back to the notes then. All right. Now, let's have you try one. Okay. Again, I kind of want to give you the opportunity to practice. Okay. So I'll do the same thing. I'll put one up on the screen and you try it. Okay. So I need you to kind of copy this one down. Right. And I'll do the same thing. I'll start working on it myself, but I want to make sure you have this one. So this one says, find the area between x cubed minus x squared plus x plus 1 and y equals 2x squared minus x plus 1. Again, no bounds on the integration, which means you have to figure out where these cross. Okay? So my questions here to you, or my directions are copy this one down, try it. Okay? Copy this one down and try it. Okay? I'll also try to put some pictures up here to help. Okay, but I won't move off of the screen until everybody has a chance to copy it. Okay, so copy these two. You're going to need to graph them to figure out where they cross, as well as which one is above the other. Okay, so copy this one down and try it. Okay, and then we'll work together on it. Okay, I'm asking you a question in the chat and I'm showing you a picture of my graph. Okay. Also, everybody see the cubic is your top function. Okay, keep working, see if you can get a value. All right, and I'll be working up here on the screen in case you want to follow along with what I'm doing. How we doing? Anyone stuck? Okay, we got somebody who got a quarter. I got a quarter. Anyone else stuck somewhere else? Again, I'm showing you the calculus method here, 0.25, good. That's the same as a quarter. Terrific. Anybody try it with the calculator? Okay, that's what you got with the calculator, Mary? That's great. Okay. Again, situations where you bring square roots, okay, so when you have fractional powers on some of your functions or logs, those are the situations where the calculator is not going to give you an exact answer. Okay, so with those types of functions, it's probably better if you try it the long way, okay? All right, anybody questions on this one? Questions about the process, questions about how we got any of the answers? All right. I know some of you are probably still working, but remember, I'm going to put all of these materials into our course along with the video. So you'll be able to go back and, double check and work through the steps. Okay. What I would like to do at this point is go back to the notes. I want to show you one more situation. Okay. And then I kind of want to show you an application that's related to economics. Okay. You might have even seen these in your econ classes. Okay, so let's go back to the notes. And over here, I have a region that's enclosed by two curves, a quadratic and a linear, and it's on an interval from 0 to 4. This is another way they might show you the bounds of the integration. They might actually show it to you in interval notation. In that case, you're going to look at 0 as your lower bound and 4 as your upper bound. I'm trying to, again, show you the different ways these problems might be posed. Okay? So we're going to graph the two curves. And again, I'm using my intersect feature or Desmos or whatever. And I notice, hey, these two curves cross, but look at what happens on the first part of the interval from 0 to the intersection point, which looks like it's 3. From 0 to 3, the linear is the top curve. Then from 3 to 4, the quadratic is the top curve. So they switch places. Okay, this is something that requires you to break the integral into two separate integrals. Okay, remember we had that property where you could pick a point in the middle of a given interval and basically go from lower bound to that point in the first integral, then from that point to the upper bound in the second integral. We're going to use that here. Also, we're going to switch G and F in the second integral because now my quadratic's on top. Here, my linear is on top. Okay? So let's see how I'm going to build the integral. Okay? I'm going to split it into two parts, one from 0 to 3 to cover this pink area. Okay? And in that example, okay, I have the linear, which was y equals x, first, because the linear is the upper function, minus the lower function, which is the quadratic. Okay. Then again, on the second part of the integral, which goes from 3 to 4, I want to get the area of this little blue piece. Here, the quadratic is the higher function, so the quadratic comes first, minus the linear. Okay. So again, I'm trying to show you what happens when you split the integral like this. So let me stop and ask, okay, does the split integral, the divided integral make sense? So do the two integrals and their bounds make sense? Okay, just give me a yes or a no. Okay, and if you have a no, ask me a question about it, okay? This is why it's critical to show yourself a picture. Okay, draw a picture in Desmos or on the TI. Okay, you've got to be able to see this. Okay, good. We can keep going. Right. So the area is, again, I'm doing a little bit of algebra. Okay, this gives me negative x squared, okay, plus 2x. So I have 3 x's and a negative x squared. So negative x squared plus 3x, just a little bit of algebra here. And over here, I have x squared minus 2x's minus another x, so x squared minus 3x. So I'm just simplifying that subtraction to make the integration a little easier. And then integrating, this gives me negative x cubed over 3, and this gives me 3x squared over 2. Okay, that's evaluated from 3 to 0. This one gives me x cubed over 3 and negative 3x squared over 2. And that's evaluated from 3 to 4. The rest is just plugging in the bounds, okay? So this is going to be negative, this is 3 cubed, that's going to be 27 thirds, negative 27 thirds, plus, which is 9, negative 9, plus 27 halves, okay? This lower bound, thank goodness, is all zeros. When I plug them in, I get just 0. And over here, I get 64 thirds minus 24, then minus 9 plus 27 halves. So this all works out to be 19 thirds as the area between the two curves. And again, remember, part of the area is with a linear on the bottom, part of the area is with a quadratic on the bottom, okay? So you've just got to split it into pieces, okay? So again, I'm not necessarily, we'll see if we have time to work an example like this, because I really want to get to the economics part. So let me just ask, does this example make sense? Okay, again, once you do the calculus part right here, the rest of it is just evaluating things with your calculator. And it's error prone, okay? It's kind of like keeping numbers straight in accounting. You have a sign off somewhere, your whole total is off a little, okay? But it's no more complicated than keeping track of signs. Okay. Let's take a look then at an application, and this application comes from economics. Okay, it's called Consumer and Producer Surplus, okay, which some of you may have heard about in your econ classes. So in general, okay, the market determines the price that a product is sold at, and the point where your supply and demand curve intersect for a product gives you something called equilibrium price, okay? So the demand and the supply kind of cooperate together to keep this price at, you know, a stable value. Consumers will purchase the same amount of a product that manufacturers have to sell. Okay, now, in reality, let's take a look at this. Okay, so let's look at my graph here. This is my demand curve, this curved line. Okay, and it's basically in terms of quantity demanded. Okay, this dot I have here is my equilibrium price, P0. Okay, and this is called equilibrium quantity, Q0. So this point, okay, between the equilibrium price and my demand curve, which is also a price, okay, this pink area, actually the amount above the equilibrium price that consumers would be willing to pay for your product. Okay? So you can think of basically the difference between this higher price on the demand curve and the equilibrium price can be thought of as a savings that the consumer realizes. It's called a consumer surplus. So for example, let's say here's the market price of a piece of technology like a smartwatch, okay? Maybe I really, really like this smartwatch and I'd be willing to pay more for it than the market price. But the fact that it's being offered at market price means I realize the savings, right, of what I would have spent on it had the price been higher. Okay, so here's how you figure out consumer surplus. You're using exactly the same strategy we use to find the area between two curves. Only here, you notice your demand curve is the higher curve. So D of Q comes first, okay? P0, it's a constant, right? So it's a horizontal line, okay, but it's still a Y value. So you're gonna put P0 here, okay? And then we would integrate this with respect to Q, because Q is our variable of integration or quantity demanded. And we're going to integrate it from 0 to the equilibrium quantity. Okay, so does everybody see how my integral matches the picture? Okay. Okay, see how the integral matches the picture. Anybody have any questions about any of the terminology I'm using? Okay. Again, I'm trying not to get into an entire econ lesson, but I will explain some of the terminology if it's not making sense. So basically, if they give you some of these values like equilibrium price, or more importantly, they give you equilibrium quantity and a price equation. So you would figure out the equilibrium price. It's whatever the price of the commodity is at the equilibrium quantity. Okay, so you could figure that out yourself. And they'd give you a demand curve, right? So basically, you'd have all the information you would need in order to evaluate the integral. Okay. So if everybody's all right with that concept, let me kind of move on to producer surplus, okay? So suppose some manufacturers would be willing to supply a price at a price lower than the equilibrium price. In other words, I'll undercut the equilibrium price, right? I might lose money, but then again, who knows? The difference between the equilibrium price and the supply curve, okay, is called the producer's surplus. It's like added income for the producer. So here's a picture that goes with that. Again, you see equilibrium price here, equilibrium quantity here. Here, the supply curve is below the equilibrium price. Okay, so if you wanted to find that integral, you would put the equilibrium price first because it's the higher of the two function values, even though it's constant, right? See, it's above the supply curve. And then you subtract the supply curve and integrate from 0 to Q0. Okay? That would give you the area, the pink area here, which is called producer's surplus. Okay? Is everybody kind of okay with this? Do you want to see an example? I know we're at an hour and 20 minutes, but let me ask, okay? Do you want to see an example? Okay, just give me a vote, yes or no. Okay, no if you're good with the concept, yes if you want to see a worked out example. Okay, let's see if we can get most of you to vote. There are 8 of you on, so let's at least get 4 of you to respond, okay? Yay. Okay, I've got 4 yeses. Okay, so we'll go ahead with the example. Okay. Now, in this example, okay, we're talking about a commodity called oat bran. Okay, it's kind of a grain type product that might be used in making bread or other types of food. Okay, so suppose I have a demand curve for that, a price that says, remember D of Q is a price, that says the price in dollars per ton is 400 minus E to the Q over 2. Okay, so that's my model for price when Q tons of it are demanded. And let's say I also have a supply curve for this that says the supply gives the price in dollars per ton when the supply is Q tons, and that's this. Now, you've got a demand curve, you've got a supply curve. Where's equilibrium on that? It's where the two curves are equal, okay? They're asking you to find consumer surplus and producer's surplus. But the first thing you got to do is figure out equilibrium quantity, okay? Remember, both of these equations are functions of Q. So what I want to do is I want to find out what is Q when demand equals supply. In other words, what's Q0, the equilibrium quantity? Okay, so I'm going to do that by setting them equal to each other, okay? So remember, here's the surplus, the supply curve, here's the demand curve, okay? And now you've got this exponential thing going on. What I'm going to try to do is get all of the expressions with Q on one side and all of the other expressions on the other side. So what I'm doing is adding e to the Q divided by 2 to both sides to get that over here. Okay, it'll be positive when I add it to this side, so I'll have 2 of them, right? 2e to the Q over 2 minus 1 equals 400. Then I'm going to add 1 to both sides, okay? So now I have 2e to the Q over 2 equals 401. Okay, so Q things on one side, number on the other. Okay, the next thing I'm going to do is divide out this 2 from both sides. So it disappears over here. It becomes a 1. 2 divided by 2 is a 1. And I'm going to leave this as 401 over 2. Notice I'm not evaluating until the very last step, because evaluating as you go along on a calculator tends to introduce a rounding error. So I'm waiting till the very end. Okay. Now you might remember from college algebra, if you're trying to solve an exponential, okay, one of the things you have to do in order to make that happen is to take logs of both sides. Since my base is e, I'm not going to use log, I'm going to use ln. So I'm taking ln of this side and ln of the other side. Okay, so take logs of both sides. Now remember what ln is saying. It's saying, what do I have to raise e to in order to get e to the Q over 2? Well, the answer is Q over 2. Okay, so this expression just gives me the exponent on e. Okay? This, on the other hand, is just a number, and I'm not ready to evaluate it yet. Okay? Last step, multiply both sides by 2, and I get Q equals 2 ln 401 over 2, which if you evaluate it on your calculator is about 10.6. Let me stop at this point and ask, is everybody okay with the algebra? Okay, we are not doing calculus here. We are doing algebra. Is everybody all right with the steps that get me to 10.6? So that's my equilibrium quantity. Okay, and again, this is stuff from Math 151. Just solving an exponential. Questions? We're good. So equilibrium quantity is 10.6. Since the quantity of the equilibrium quantity and price go hand in hand, I can use either the supply or demand equation to find the price. Okay, so I am plugging it into the supply equation and use all of the decimal places in your equilibrium quantity, okay, to make sure you get the right price. Okay, you want it accurate to dollars and cents. So notice I'm plugging in 10.60163, okay, which is my entire value that I got for Q0. Okay, and this gives me an equilibrium price of $199.50 per ton for the oak brand. Okay, when 10.6 tons is demanded. So everybody all right with the P0 and the Q0 values? Okay, so we've got P0 and Q0. Okay. So those are my equilibrium price and equilibrium quantity. And again, you can use either supply or demand function to compute that price. Now, if I want to do consumer surplus, remember that's if the price above P0 that a consumer would be willing to pay for your product. So the demand curve goes first, minus P0. So here's my demand equation, 400 minus e to the Q divided by 2, minus this is my P0. And I'm integrating that from 0 to 10.6, 0163. So again, to basically do that, if I'm integrating these, okay, let's do some subtraction here. 400 minus 199.50 is 250. And then here I'm just doing an integral. Okay. Remember, this one is a constant. So it's as if I had Q to the 0 multiplying it, okay? So I'm going to add 1 to that 0 and put it over 1. So here's where the cube pops into existence here. So I get 200.5 cubed, all right? You might remember with this one, okay, you basically are going to wind up with the same exponential over the k in the exponent. So that would be over 1/2, okay, which then flips up to give me a 2, okay? Dividing by 1/2 is multiplying by 2. So that's where this 2e to the q divided by 2 came from, right? Then you're just evaluating it at the 2 bounds, okay? So I'm plugging in my upper bound minus my lower bound, okay? And I get a consumer surplus of $1,726.63, okay? So what that means is, okay, at equilibrium price, this saves the consumer $1,726.63, okay, on the price of the oat bran. Okay. So that's that one. Producer surplus is very similar, except you're switching the order of P0 and you're using the supply curve instead. Okay, but it is a similar process. Okay, and it's the same. This expression is similar. Okay, the producer surplus is the same value in this case. Okay, that's not normally what happens. Okay, usually producer and consumer surplus are not the same value. But basically, just make sure, because there are probably some applied problems, okay? Are you okay with computing, with the way this is computed? Okay. Are you okay with the computations? Again, there are formulas for this. They're in the text. They're in my notes. If you do help me solve this or show me an example, it'll show you the formula for producer surplus and consumer surplus. Okay. So we're okay with this? Anybody questions? Okay, I'm going to stop sharing my screen and go back to the meeting at this point. All right, and let me ask you at this point, any questions on anything? Anybody have any questions on any of the stuff we covered? Good. And again, of course, when you're trying these problems in section 15.5 for homework, if you get stuck on anything or something's not making sense, please feel free to email me and I'll walk you through the problem, okay? Again, there's that little help menu at the top right, and the last one says ask my instructor, just ask me. When we meet again, okay, we're going to be talking about some additional integration techniques. We'll be moving into chapter 16. Okay, so I'm going to stop my video right